Good morning, this is Miss Billerbeck, and we are going to talk about 6.2 exponential functions. So if we have a function f of x equals a times b to the x, this is an exponential function where a is the initial amount. So at x equals 0, that would make b to the x 1. So a would be the y-intercept. Then b is the constant ratio. So this is only the y-intercept should there not be anything added to the function, by the way. All right, so then b is the constant ratio. Okay, so let's talk about what b is. So b cannot be greater than, or b has to be greater than 0, because if this was 0 to the x, well, 0 to the x equals 0, except in the case of 0 to the 0. Then it is undefined. Okay, so it's undefined. When mathematicians agree to disagree, they call something undefined. So we know that 0 times anything is 0. So we also know that a to the 0 equals 1. So there's been a discussion about whether this was 0 or 1. So they agreed to disagree and called it undefined. So that's why 0 to the 0 is undefined. Okay, so then we can't have b equaling 1. So let's take a look at what happens when b equals 1. So if I have 1 to infinity and beyond, I have that equals 1. Okay, if I have 1 to the 0, that still equals 1. If it's 1 to the negative 1, that's still 1. So it just doesn't matter. I've got a constant function if b is 0 or if b is 1. So that means that I have a horizontal line at for the values of 0 and 1. So that is definitely not an exponential function. So that's why those two values, 0 and 1, are ruled out for b. So now let's talk about what b is. So b is the constant ratio. So that's the next term, xn, over the previous term. So that means it's just one away from the next term by when I say n minus 1. So remember, subscripts are not exponents, they are names. So this is set, you say x to the n, or xn, not x to the n, xn over xn minus 1. So that's a name. So that just equals the previous number over the number. Okay? So this, if this was the first number, that's the next number. Okay? So that's all b is, the constant ratio. All right, so let's take a look and explore some exponential functions. All right, so first we should probably do a table and try to experiment with some of these values. So if I'm going to have x, I'm going to have f of x, and f of x equals, and for this one, if we have f of x is b to the x and b equals 2, we're going to say 2 to the x. All right, so let's put in a few values. We'll do negative 2, negative, actually, negative 2, negative 1, 0, 1, 2. Okay, and we'll put in 2 to the negative 2. So 2 to the negative 2 just means the negative is a locational exponent. So that means I have 1 over 2 squared, which is 1/4. Okay, 2 to the negative 1, that's just an inverse, is just 1 over 2. and 2 to the 0 we know equals 1. And then we have 2 to the 1, which is just 2, and 2 squared, which is 4. So now we have some points that we can graph on a graph. So let's take a look at a graph. There we go. Okay, so for the first one, let's plot. We have -2. We had 1/4. So we'll just make an estimate about where 1/4 is. -1's 1/2. That's easier to estimate. 0 is at 1. So see how that's hitting the y-axis, and why I would call it a y-intercept. As long as we don't have any shifting going on, vertical shifting, that's a y-intercept. And then at 1, we're at 2. So instead of it was looking like a line for a moment there, but now we're getting in the critical points here. So then at 2, we're up at 4, and now we see a really huge shift. And we might ask, well, what's happening at 3? Because things are changing rather fast. So if we try 3, so that would be 2 to the 3rd equals 8. So we see, wow, that's really shifting. So 3 goes all the way up to 8. So now if we draw this exponential curve, we're going to come in like this and then slowly stretch away from the x-axis, and then we're going to shoot up, straight up, and then it's just going to go so fast upward from there. And that's just what exponential functions do. All right, so let's examine what we're looking at here. Right, so if we look at this, we see, well, this line here, it never goes and hits x equals 0. So when we look at this data here, it's just going to get smaller and smaller and smaller, but it's never going to be 0. So 0, x equals 0, or actually f of x equals 0, is never going to happen. So that's what we call an asymptote. So I'm going to make the asymptote a red line, a dashed line. Okay, so this is like a force field. If you're like into sci-fi, it's like you can't ever get through it. It's there, it's blocking that curve. You can get really close, but you can never be in it. Okay, so this fancy word for this line right here that I drew, that one right there, is called an asymptote. Okay, so that's like that force field line that doesn't let the graph ever cross. Okay, so it's approaching that, but we see that as x increases, y increases. So this is called an increasing function. Okay, we see that the x domain, even though this is going straight up, it's going to go straight up and keep heading that way. So x, the domain for this one, is going to be all real numbers again. So use the fancy R to look cool. Okay. Here, let me move this so we can see what I'm writing. Sorry about that. Okay, so the domain for this is R, all real numbers. You see the A, all with the little L, so that's all. The R is real, and then we're kind of making a number sign. So it's a super cool math symbol for all real numbers. I'll write that down, all real numbers. Okay, so just remember that. So So the range, well, we see the range is restricted. The range can't be 0, so, but it's only greater than 0, so we would write y is greater than 0 for the range. All right, we also see something interesting right here. We have a y-intercept. Now, if we take the function apart, we were talking about f of x equals 1 times 2 to the x. We didn't write the 1 because why? It would waste ink. But this is actually a times b of x, okay? So now we know that a equals 1, and look, we're going through 1 right there, okay? So that is our y-intercept. So this is acting like a y-intercept. And the only caveat is if I had something added to this function, that would change that a bit. Okay, so we can talk about that as an initial value. So that's an initial value. All right, so we've really broken that one up. Let's take a look at the next function we were asked to look at. Okay, so let's make a similar table. We have x and we have f of x. And this time it's going to be 1/2 to the x. So if we use the same numbers here, this time I'm going to use this because I know something about this. So we'll use similar numbers, but not quite the same. So if I have 1/2 to the -3, that negative means I can flip that over. So I have 2 over 1 to the third. Well, that's just 2 to the third, which is 8. Okay, if I have 1/2, and that's -2, that's just 2 squared, which is 4. If I have 1/2 to the -1, that just means do the reciprocal. -1 means do the reciprocal, which is 2 over 1. So that's just 2. And then 1/2 to the 0 is, of course, just 1. And then 1/2 to the 1 is itself. And then 1/2 squared equals 1/4. Okay, so let's use that now, and we'll use the same graph and see what happens with these points. Okay, so I'm going to use a different color here. So now we see at -3, we're at 8. So -3 is here, that's our 8 right there. -2, we're at 4. -1 is 2. Then at 0, we're at 1, so that's the same as the other one. And 1, we're at 1/2, so we're slowing down our descent. And 2 is 1/4, so we're approaching that asymptote, but we're not going to ever reach it. Okay, so now let's connect all our points. So this one we're zooming away from up here, and it's a decreasing like a lunar lander landing on Mars. Or a lunar lander means the moon, so a lunar lander landing on the moon. So it's just decreasing. Well, actually, the lunar lander actually lands on the moon, but we're not going to. So we're just going to do a flyby on the moon and not quite touch down. because the asymptote is keeping us from touching down, right? So we see that this is a decreasing function. So as x increases, y decreases. So we would write decreasing. Okay, so we see we have the same y-intercept. Okay, we see we have a range. The domain is also all real numbers. This is going this direction, just like the other one. And our range is actually the same too. So it's everything greater than 0 for y. So their domain and range are the same. It's just this is reflected around the y-axis. Okay, so that's very interesting. Okay, so we see very similar things with these, except for a reflection around the y-axis. All right, so let's take a look at some other problems. Yay. Okay, so this one here, this is a real life problem, like a problem. I'm not just saying it's a real life problem, it's a real problem. Okay, so a network administrator uses a function f of x equals 5 to the x to model the number of computers to which a virus spread after x hours. So this is time, hours. How long will it take this virus to spread to 50,000 computers? Okay, so this might take a little work. So let's do a bit of a chart work really quickly and get a grip on what's happening here. So we have 5 to the x. So time can never be negative. So we're going to start with 0, 1, 2, 3, 4, 5. I guess I should have made this closer. So let's do that. So 1, 2, the one more in the middle, 3, 4, 5, and 6, and 7. There we go. All right. So at 0, 5 to the 0 is just, there's just one computer that's infected. Okay, that would make sense because you can't get infected if there aren't any computers infected. Okay, so 5 to the first means now after 1 hour, 5 computers are infected. Okay, after 2 hours, we have 25 computers infected. After 3 hours, we have 125 infected. After 4, we have 625 infected. Okay, after 5 hours, let's see, 625 times 5, we have 3125. Ooh, that's only 5 hours later. Look at all those computers infected. And let's do 6 hours. Oh my goodness, I have to write this sideways. It's getting so big. 15,625 computers are infected. And let's see what happens after 7 hours. 78,000 computers, 78,125 computers. Wow. But it wants to know how long it'll spread to 50,000 computers. Well, that's kind of harsh, isn't it? Because you kind of have to have one of my graphing calculators to do this. So let's learn how to use a graphing calculator. So with this one, we have a key here for exponent. Okay, we also know we have this. So let me clear this and show you how I did that. So we know that it's 5, and then the base is 5, and our exponent is x. So I'm going to hit alpha x because there's a green x over the key. So I'm going to hit the green one, and now look, I have 5 to the x. Okay, so I've already been in here and set up my tables. So let's graph it really quickly so you can see how cool graphing calculators are. Here we go. I'm going to hit graph. There it is. That's the graph. How fast virus will spread amongst computers. Okay, so, but this doesn't really tell me how many are going to be there, how many computers are going to be infected, or how long it'll take to infect 50,000 computers. So let's go second table. And I've set this up ahead of time to save some time, but you can see right here, looking at this, I'm going to have to stand up a bit, but we're right here at 48,206 here is about 6.7, and 6.8 is a little over 50,000. So we're about 6.73 hours it would take to infect 50,000 computers. So of course you couldn't get that accurate without one of these graphing calculators. And there are online graphing calculators, by the way, so there you have it. All right, so let's go on to, let me write down the answer so you see. The answer was 6.75 or 3 hours. That's how long it would take. Pretty crazy. 50,000 computers. All right. So now let's look at, if we're given points, can we actually make an exponential function? So we know we're using this function f of x equals a, and that's times b to the x. Okay, so we are given x and f of x right here. So from plugging in two of the points, we can figure out certain values, okay, without actually knowing a and b at first. So first we're going to have 3. Let me write it up here. We have 3 equals a times b to the 0. Oh, wait a minute. What's b to the 0? It doesn't matter what b is, does it? Unless b is 0, but it's not. So we're going to say that this is 3 equals a, because b to the 0 equals 1. So this is just a times 1. So now we have a. So now we move to the next easiest one right here. And we write f of x, which is 12, equals a times b to the 1. Oh, wait, b to the 1 is, oh, we know a already, so we don't have to write that. A is 3. So b to the first is just b, so that's just 3b. So if we take 12 and we have 3b, we just divide that by 3. Divide each side by its multiplicative inverse, and look what we have. B is 4. So now we have f of x equals a is 3 times 4 to the x. Okay, so that's how we'd get the first one. But one thing I didn't do that I probably should have done before I even started this is I assumed this was an exponential function because it said write an exponential function. But what would have happened if they fooled me and it wasn't an exponential function? So let me show you how you would check that. So let me just erase this part right here. So remember how you have to do the next term over the previous term? Okay, so I have 12 over 3 and 48 over 12. and 192 over 48, and 768 over 192. And what would that be? That equals 4. Okay, so 4 is B. So there's another way to find B besides how I just did it. Okay, although I like how I do it, but you could have found B this way. All right, so let's use this way to find the B for this one. All right, so first we're trying to find B, so the second way I showed you. So we're going to divide this, and that should equal 243 over 729, and that should equal 81 over 243, and that should equal 27 over 81. All right, so we need to figure out, well, what is this? So we know that, hey, I could take 127 out of here, and that equals 3. So it looks like it's going to be 1/3. So it's easiest on the littlest one. We always know that 12 divided by 3 is 4. So then you just multiply that by 4. Is that true? That is going to be 768. So now that we know this is 3 times, this is 3 times 729. We multiply that. 3 times 9 is 27, carry 2. 3 times 2 is 8, or 6 plus 2 is 8, and then 3 times 7 is 21. Okay, so we see, oh, hey, and I wrote that backwards. Good thing I did that. Check. So we want previous term over that. So sorry about that. Don't do what I just did. Okay, see how they have to be 1/3 there. So previous term by next over the former term. Okay, so and it's really it's tempting to put the bigger number on top, just like I did there. So don't do that. Okay, so now if we solve it the other way that I used to do it, is we have f of x is 2187 equals a times b, and x is 0. So we know that's a times 1. So now we know that 2187 equals a. So we know how the function starts. Now, if we use the technique that I showed you to find b, so we have this is 729, so we'll use the second point, equals, we have 2187 here, times b to the 1. So I'm using this coordinate point right here. Okay, so that's my f of x, that's my x. Okay, so now I know b to the 1 is just b, so I just divide by 2187. And that gives me b equals 1/3. So that's how I always do exponential functions. But if you want to make a common ratio, make sure it's an exponential function. This is the way to do it. All right, so we had this function for the first one. So now let's take a look at it. We put it all together. We have this for our function. So 2187 times 1/3 to the x. Okay, so let me write that a little bigger because it got squished. So we have f of x equals 2187 times 1/3 to the x. And that is our exponential function. So from what we saw in the last example, when we looked at this one was f of x equals 2 to the x. And this one was f of x. Set this down, it's a little easier to write. F of x equals 1/2 to the x. So we can see we have a decreasing function when it's a fraction. When it's less than 1 and between 1 and 0, it's a decreasing fraction. And it's an increase or decreasing exponential function. It's an increasing exponential function if it's greater than 1. If the common ratio is greater than 1, it's an increasing function. So now let's take a look at this. From learning that, okay, is this an increasing or decreasing function? Well, b is greater than 1, so this is an increasing function. This one, b, is between 0 and 1, so that's a decreasing function. Decreasing. All right, so there you have it. Let's do another one here. Okay, so we want to identify each function as linear or exponential and explain. Okay, so we have a tree, and the tree is going to start like this. So we have 1, 2, 3, and 4. Okay, so the next level of tree, so this is at tree 0. This would be at x is 0. At the first value, then we split up into 4. And then this is 4. Actually, let me make this a little hard with this space, but let's make this, I'll make it like that. And then this is 4. And then we finally have this 4. Okay, so this happened at 2. So you can see where this is going. Okay, so each time we're going to increase by 4, and this is going to get to be huge. I can't even fit it on this already, on the third one. Okay, reason being is it's 4. So 4 to the 0 is just 1. 4 to the first is 4. 4 squared is 16. So we saw, oh, if we counted this, we'd have 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the reason why I can't draw 4 to the third is that's now 64 branches. So this one is definitely exponential. Okay. So let's take a look at another one. Oh, and we have a constant ratio of 4, by the way, on this one. So our b, let me go back to that really quickly. So b equals 4. So we could say this is f of x. If we want to write an equation as 4 to the x. Okay? So that definitely would fit this tree diagram. All right, so let's take a look at this one. So we have f of x equals the number of boxes in a row of x of a stack in which each row increases by 2 boxes. So if I start off with 1 box, the next row will have 2 more boxes. Okay, the next row is going to have 2 more boxes. And the next row is going to have 2 more boxes. Okay, we could keep going here for quite some time. Okay, does this look like an exponential equation? If it was an exponential equation, we'd be going from here to maybe 9 boxes the next time. Okay, so this one has a common difference, not a common ratio. This is a common difference of 2. It doesn't have not a common ratio. Okay, so if it doesn't have a common ratio, we're looking at a linear function. So if it's changing by 2 each time, and we're starting, if we start with 0, well, let's see, we start with 1 box, so we'd have something like f of x equals, and we can always test it, is 2 times x plus 1. It'd be something like that, because we started with 1 box. So this would be at times 0, but then we have to subtract, that's not times 0, so that's at time 1. No, actually that is times 0, starts with that. So we'd have something that looks like that, because after time 0, this would be the second moment. So, so we would have, if x is 1 for this one, 2, and 3. So 2 plus 1 is 3. 2 times 2 is 5. And then 2 times 3 would give us 1, 2, 3, 4, 5, 6, 7. Okay? So that'd be a linear function. All right, that's it. Have a wonderful day. Bye-bye.